Hello everyone. In this module, we can discuss the concept of Huffman coding procedure by taking an example. In the given example, here a discrete memoryless source has an alphabet of 7 symbols with the properties for its output described in the table. So here they have considered 6 number of symbols in a particular alphabet that range from S0 to S6. That is total of 7 symbols. And here the respective properties are also given for each and every symbol. If you take the sum of all the properties from S0 to S6, it will be equal to 1. And in the example, it is given M is equal to 2. In the Shannon-Vanna coding procedure, M represents the partitioning value, and in the case of Huffman coding procedure, M is a merging value. So here M is given as 2 bits per letter. Consider 0 and 1 during the reduction process. While merging, you have to assign 0 to the upper set and 1 to the lower probability symbol. And here they asked you to calculate the efficiency by using the Huffman coding procedure. The first step in Huffman as well as Shannon-Vanna coding procedure is same. That is, you have to represent all the symbols in the non-decreasing probability, that is decreasing order probability. In the given example itself, all the probabilities are shown in the decreasing order. If you observe, it is from 0.25 to 0.0625. So it is in the decreasing order only. So we have represented in the stage 1. In the Shannon-Vanna coding procedure, we have partitioned the probabilities, but here we are going to match the last 2 or least 2 probabilities. In the given example, the least 2 probabilities are S5 and S6. So let us match the 2 probabilities, 0.0625 and 0.0625. It is 0.125. And in the next stage, again you have to represent all the probabilities in the decreasing order, including the due merged value. The due merged value is 0.125. And this will be given the highest priority when compared to the existing 0.125s. So that's why this is taken to the third position. Just below 0.25, we will mention this duly added 0.125. This will be given the highest priority. And then followed by S2, S3, S4 probabilities. And in the stage 3, again, we will merge the least 2 probabilities. After merging, you have to assign 0 to the last but 1 probability and 1 to the last probability. And upon merging 0.125 and 0.125, you will get 0.25. And that 0.25, if you observe the probabilities, here we have 0.25s. 0.25s, that is S0 and S1 probability. But this newly added value will be given the highest priority. So this will be taken to the first position, 0.25, followed by 0.25 and 0.25 of S0 and S1, followed by S2 and S3. This we mentioned. And again in the stage 3, we will match the least 2 probabilities and assign 0 to the last probability, 0 to the last probability and 1 to the last probability. So like that, wherever after merging, we will provide or assign 0 to the last probability and 1 to the last probability. And in the stage 4, again, this will be given the highest priority, followed by the remaining 3 0.25s. So again, we will merge 0.25 and 0.25 last and last but 1 probabilities and assign 0 to the last but 1 and 1 to the last probability. And upon summing, you will obtain 0.5. This is the highest value, so it will be dragged to the first position, followed by this leftover 0.25s. That is written here. In the stage 5. Again, in stage 5, we will merge the last 2 probabilities and the sum is 0.5. So this will be given the highest priority. So 0.25 followed by the existing 0.5. So again, if you merge 0.5 and 0.5, you will get the merged value as 1. So up to this, we have to merge all the last 2 probabilities because M is given as 2 here. If M is given as 3, you have to merge the last 3 probabilities. And you have to assign -1, 0 and 1. So like that, the process of merging and assigning 0 to the last button and 1 to the last property, this will continue till the merging value is equal to 1. After merging, you have to identify the path of each symbol. In order to write the code word, you have to observe the path. For example, you can see the representation with the dotted lines. Here we are going to write the code word for S0. So in order to write the code word for S0, first you have to observe the path of S0 from stage 1 to stage 6. So here if you observe the path is from 0.25 and in stage 2 it is in the first position, stage 3 it is in the second position, stage 4 it is in the third position with the assigned code word as 0, and the stage 5 it is in the like first position, no assigned code word, and in the stage 6 it is assigned with a code word of 1. So if you observe the codes assigned to the S dot, it is only 0 and 1. So you have to write the code word as 1 and 0, that is in the reverse direction. First you observe the path and write the code word in the reverse direction. So like that you can update the symbol. Its probability we have written in a decreasing order, and the code word for that is observe, identify the path of each symbol and write the code word in the reverse direction. Similarly, if you observe S1, S1 is 0.25. Next it is also in the stage 2 also it is in the same position. Stage 3 it went to third position, no assigned code, and in the stage 4 it is assigned with 1. And in the stage 5 it is merged and it went to first position, and in stage 6 again it is assigned value is 1. So it is 1 1, even if you write the reverse direction it is 1 1 only. So that's why S1 code word we have represented as 1 1. Like that you will represent all the code words for 7 symbols. And next column, we will write the code word length. This is the same procedure like that of Shannon coding procedure. If you observe the length of S dot, here it has 2 symbols, 1 and 0. So that's why length is 2. And similarly, S1, the length is nothing but the number of bits available in the code word. So it is 2. And for S2, it is 3. S3 also 3. S4 also 3. S5 and S6, it is 4. Next, we will calculate the average code word length, entropy, and efficiency. We will use the same expressions as what we followed in the Shannon coding procedure. First is to calculate the average code word length, which is summation k is equal to 0 to 6. That is total of 7 symbols. Product of probability and its individual length. So sum of all the probabilities, sum of the products of probabilities and individual length is our average code word length. So 0.25 into 2 plus 0.25 into 2 plus 0.125 into 3, like that, so on, 0.0625 into 4. We obtained the average length as 2.625 bits per symbol. And next calculation is entropy. So entropy expression is summation I is equal to 0 to 6, probability into log 1 by probability base 2. Probability of each symbol we have to write. So 0.25 into log 1 by 0.25, that is 4 base 2. So like that we have written all the summations. Because 0.25 it is repeated twice, 0.125 it is repeated thrice, and 0.025 again it is repeated twice. So directly we have substituted and evaluated the entropy as 2.625 bits per cell. And code efficiency is entropy by average length. Average length into log m base 2, but because m is 2 here, log 2 base 2 will be 1. So directly you can write it as entropy by average length. So because both entropy and average length we obtained it as 2.625 into 100. So efficiency is 100% in the above example. So in this process we will calculate the efficiency for Huffman coding procedure by using the merging procedure. Thank you for listening.